Okay, hello everybody. So we have been discussing the Mohr circle. By the way, today's lecture is going to be pre-recorded, unlike the other lectures which are in the live mode, and that's because of circumstances. So hopefully by next time we will have a live class all over again. But this time it's going to be recorded lecture, and I hope you listen through all this throughout the lecture, because we are going to finish off our discussion on the Mohr circle, and that discussion is going to yield some important insights. Now, last time we have already been you've already looked at uh, uh, you've already participated, I hope, in the tutorial that was held on Monday. And before that, we were discussing Mohr circle and the conventions around it. So we were discussing how this is the shear stress axis and this is the normal stress axis, and you draw the circle on this. And this in the 2D case. The various stresses or the conditions of stress at different points of the circle are basically representative of the various stress values as you rotate through the angle here, right? So in this particular case, when you rotate by an angle phi in the counterclockwise direction, it results basically in a situation where you have to rotate this line segment in a clockwise direction, right? So this is one of the ways of doing making Mohr circle. And uh, here, interestingly, you have to see or observe that uh, the the directions of the rotations are opposite, right? So here you have a counterclockwise movement, whereas here you have a clockwise movement. There is another method in which the conventions are changed a little bit so as to allow for rotations to sync with each other, and that's one of the things we want to discuss today. So, say method 2, okay, and maybe I'll just draw. Okay. This looks more like an ellipse. Let's try to draw a circle. Yeah, okay. So now, okay, in this particular case, it differs from the first method with regards to the convention regarding the angle. Okay, so as before, the center is located at sigma xx plus sigma yy by 2. That does not change. So this center location, this is given as sigma xx plus sigma yy by 2. Okay. But now, if you have a particular situation, so if you have, let's say, this face that is given, and in this particular case you have uh, you have the sorry you have the stresses, then you have to identify the point sigma xx somewhere, right? Okay. So this is the right hand face of the cube. So you have to identify where sigma xx lies. But now, what about the sigma xy value? So let's say both of these numbers are given to you. So sigma xx is known to you, sigma xy is known to you. So first thing you do is, on this axis, you'd figure out where sigma xx is. Now sigma xy, what you will do is you will follow an opposite convention, wherein uh, for the right hand side of the face, if sigma xy is greater than 0, then it is plotted on the portion below the horizontal axis. and if xy is sigma xy is less than 0, then it is plotted above. Okay. So, when you are given this particular circumstance, you look at the value that is given to you, and then you say, okay, if this value is given to you is positive, then you locate the point here, okay, such that here sigma xy this corresponds to a greater than 0 value, and this is opposite to the idea that we were discussing before. And what this basically does, the reason this is used is because by making the sigma xy go axis, basically what you are doing is orienting this axis downward, and the advantage here is that the rotations of axis are now synced with Mohr circle. Okay. And to see this, what I have done is I have taken an image here. This is now from a book called Engineering Mechanics of Solids by Popov. Okay. So, the book by Popov. Popov is the author, and this is just a photo, right? So, this doesn't come out that well, but we'll go over the basic ideas. So, this is the cube here, and then this is the right hand face, the values of the stresses given at the right hand face. So, sigma xx and tau. Okay. So, in the books it usually is denoted as tau. I think I have discussed that before. So, now this is directed in the positive direction, this is the positive direction. So, to find this particular point, what you do is you locate sigma xx, and then you locate tau xy such that it is in the positive, this downward direction is the positive one, and so you locate this face, which means that this point AC represents this particular face right now. And if you take this particular line going through the center, then you will find a conjugate point BC. Now, this conjugate point here, this represents this particular face, the top face. Okay. And if you were to rotate this cube, so this is the cube, and now it is being rotated here by an angle theta. Okay. So, this theta now is a variable theta. Okay. So, this theta is the angle of rotation of the axis. So, this cube has now looks or is oriented along the axis. So, you now have sigma xx dash tau xy dash. So, now in that case, how do you locate the point? So, what you do is for theta rotation, this has to rotate by 2 theta. Okay. So, you rotate it at 2 theta, but you rotate it in the counterclockwise direction, just like this particular rotation. So, this rotation and this rotation are now synced. So, now here this point. So, once you do that, this particular point will now correspond to this. So, this new point corresponds to this particular case. So, now you can see that the tau xy here, this is now on the upper plane. So, this is now negative. So, they have reversed the direction of the shear stress right here. Similarly, for this particular point, right, you can look at it. Now, the reason this convention is important for us is also because the book follows this particular convention. Okay. So, there are certain example problems in the book which are very good problems to go with, and you should just take a look at those particular problems. So, what I have done is I have taken one example from the book, and This is, by the way, page 201 in my case. So they've given a cube, and then they've given you these values 110. There is a shear stress 450. There's a this the shear stress here again. This is sigma yy is given as 550, and they draw the Mohr circle, and what we will see is that since this is positive, this is has to appear here, right, on the negative side. So we see that the sigma xx, so this point is located at 110, which is the value given here. So this is also 110. So this point is located, and then you have to locate the y axis point, and that would be 450. Okay, here it says 440. I think okay, I think this number is probably incorrect. This probably should be 40. Okay, you can double check. I think this is a printing error here. Okay, so now this particular point is located here, and you have 40 and 110. So you have been able to locate this particular point, and similarly if you go on to this side, you will see that you have hit a value of this should be at 50, and right, so you see that sigma y value already they found it as 50. Okay, so given all these numbers, you can draw this circle, and then here this is being rotated at 45 degrees. So this particular, so you have to rotate this axis by 90 degrees right here. So that's what they have done, and once you rotate it at 90 degrees, then you can find the stress on this right hand face. So now this particular point should correspond to this particular face. So let's see what values they have found out. So here they have labeled it as tau AB, and tau AB, okay, they are saying it's minus 30, which that's the numerical value. So they have pointed it downwards. So obviously tau AB here is in the upward side, right? And let's see what other value can we read of right here. So sigma a is the value here, and sigma a is 120. So now you can see that that is a positive value. So you put a positive value right here. Okay, so you can read off other points also, and find and find for example sigma b here, which is sigma yy. That's this point is probably number 40, so 40 megapascals, right? So so we see how this this Mohr circle comes about. Okay, so this is the convention that the book takes, and I believe there are maybe there's one more sample problem in there. So you should go in and take a look at these problems definitely. That will be extremely helpful for you. Okay, okay. So let's see. Is there anything else that is left? Okay, so now maybe we should come to strain. Okay, no, to add. So we have discussed. Okay, one more quick thing, which is, see, in a given body. Okay, so we see have a given body. We have at every particular point you will have a stress tensor associated with it, right? Now that you have this stress tensor associated with it, this can be represented as a matrix, right? So this is a matrix 3 cross 3. Now this stress tensor, so you have to usually find values for these numbers. Now this values, numerical values here cannot be found out till you tell people as to what is the axis. Okay. So, without giving this axis, this the numerical value for this cannot be found. So, as you rotate this axis, this numerical value will keep on changing, but that does not mean that the stress situation is changing, right. I mean, this body is experiencing this, whatever this body is, the state of stress is there, it does not know what value of what orientation you want to choose. So, this matrix keeps on changing, but it is all of these are representing the same state of stress. So, numerically you can have many different infinite number of values here, of course, as the transformation goes. The transformation, of course, there is a strict rule about the transformation, but the stress tensor or the state of stress is the same in all cases. Okay. So, now that we have discussed stress, what we have left out is strain, right, and we had seen earlier that the strain is a tensor also, and let me quickly go back, see where it was discussed. Okay. So, we had discussed strain here, and we had seen how the strain tensor has components of epsilon xx, epsilon yy, and then you have a shear component as well, right. So, if the state of the stress tensor is dependent on this on the axes, then the state of the which is usually written as E. Wait a second. The strain tensor should also follow some similar rules, right? And we have seen the how the stress tensor transforms, but what about strain itself? Okay. Now, we had the question is again very simple, which is if you have an axis and then you have a new axis which is at theta. Then how does this transformation affect my calculation of the strain tensor? Now, if you remember, we had spoken about the transformation matrix, and we can write x dash y dash as cosine theta sin theta. I am again taking a simple two dimensional case, sin theta cosine theta, and this is x y, okay. And then you have, so this implies I am just going to write this down because we are going to use some of this today, sin theta cosine theta. I have just flipped this, right. So, I am writing down all the relationships that I might need, and similarly for displacements, right. So, displacements will also have the same, sorry, this is v dash is equal to cosine theta sin theta minus sin theta cosine theta. Okay. So, u and v are my displacements in the xy coordinate system, and u dash v dash are my displacements in the x dash y dash coordinate system. And so, the question is, what we are trying to find out is the relationship between epsilon xx dash and epsilon xx. We want to know the relationship between these two, right. So, let us see uh, from our formula we know that epsilon xx was my del u del x, right, and hence similarly epsilon xx dash will be del u dash del x dash, okay. And by using a chain rule I can see, I know the relationship between x and x dash, which is why I am breaking this up into this kind of a chain rule. Okay. Wait, I have missed something. There's a dash here, right? Okay. So this implies my epsilon xx dash is equal to. Now I can just go ahead and I can replace. So I know what u dash is in terms of u. So I know that u dash is u cosine theta plus v sine theta, okay, and dx by x dash. So I have to replace del x dash. So see, I had flipped it because of that. So from this transformation I can get that value, which is now going to be x dash cosine theta minus y dash sine theta, okay, plus the other term, which is again which will be again u cosine theta plus v sine theta, and then del x dash. Sorry, wait. This is del x dash, and this is y. So y will now be x sine theta plus y dash. Just a second. Okay, so my y is x sine theta, y dash cosine theta, right. Okay. So now what I should go ahead and expand, and this is going to be a lot of terms here. So let's see. So let me see, this term, this multiplied by this x will go away. This will be left with del u by del x, then cos square theta plus del v by del x sine theta cosine theta, okay, and then we should have, from here we will have del, similarly we'll have a del u by del y sine theta cosine theta, one term will cancel, del okay, one term will cancel, and then I should have on this side we'll have del v by del y sine square theta, right? Okay, so please double check if I've gotten this right. What I can do is I can combine these two together as sine theta cosine theta. Okay. Okay. So now this is okay. So we know that this is nothing but epsilon xx. This term here, this is my gamma xy, and this is epsilon yy. Okay, so this basically implies that epsilon xx dash is equal to epsilon xx cosine square theta plus epsilon y sine square theta plus gamma xy cosine theta sine theta. Okay. This should seem similar to something you have encountered before. Okay, let's just go and search for it. It must be here somewhere. Okay, so this is the term I was looking for. I'm just going to copy this. Okay, so and I'll just copy this as well to the other page. Okay, no, wait. Okay, nice. So now compare these two equations. Wait a second. Okay, compare these two equations. The thing that does stand out is this number 2. Okay, so here here you don't have this coefficient of 2, the coefficient is just 1, but here you have a coefficient of 2. This should resonate with you because this is similar to the transformation that we had already discussed, that the shear strain is written as gamma xy by 2, but when you evaluate it in the matrix, it is gamma xy by 2, right? So we already know that, and then this factor of 2 basically takes care of that. Okay. So so now we can write down our other equations. So basically this translates to, and I'm just going to give you the formula for this, which is it's basically exactly the same. It looks exactly the same as the previous form. Of course, the similarity should not come as a surprise. They're just tensors. They're just going to transform the same way. So in fact, if you were to consider, if you were to just look at the strain tensor, then this form becomes just rather obvious, right? That this is going to transform like this, right? So now a couple of things I'm going to leave out for you, which is show that the maximum and minimum, which are the basically the principal strains for the system. Sorry. So that the maximum and the minimum strain, which we'll call, let's say, epsilon 1 and epsilon 2, they are epsilon 1 comma epsilon 2 is basically, this is left as an exercise. This is exactly the same as before. Of course, there's no change in the formulation, which is why I'm not going over it. Okay. So this is the formulation that the principal strains. So there are two principal strains in the two-dimensional case, and just like before, there is no shear strain associated with a situation where there's only the principal strains. Right. Okay. So now you should be able to draw. So the stress and the strain seem to have a lot of similarity, and they should, right? So you will see that again you can draw a circle just like the previous case. So you have a Mohr circle of strain, okay, and in the Mohr circle of strain is the same idea where when the only difference being that this axis is now, okay, so this is and there is no other difference. It's the same idea all over again. So we don't have to go into this the Mohr circle of strain, because it's just a repeat of the same old the same old idea. Okay, so other than that, have I missed anything? Okay, just like plane stress problem, there is something called plane strain, and in plane strain you have you'll have one of the directions which will not matter. So if z is that direction, then you will have this condition. Okay, so the plane strain condition is this, which is exactly again very similar to the plane strain problem. Okay, let's see how much time is left. Okay, we have quite some time. So one thing that we will not go through, although the book does go through it, is the generalized Mohr circle. So we are not that much interested in going through the generalized Mohr circle so much, because in case of three-dimensional systems, I believe it is easier see, Mohr circle was essentially a very simple graphical way of examining things at a point of time. That time is well sort of past now, because you have calculators that will do matrix calculations, right? So if you know the transformation, all you need to do is to multiply the strain tensor by the appropriate transformation matrix to get the new one. So for three-dimensional cases, it does not make enough sense to go and learn the generalized Mohr circle. At least in my opinion, it doesn't make that much sense to go all over it, because you don't learn something new. In fact, it's easier to understand and visualize a lot of things if you were to just look at it as a matrix operation. Right? Okay, so that has sort of brought us to an end of this particular chapter. The homework has also been uploaded for you, so you should go over it and try to submit it. If you have any questions, let us know over email, and we'll try to answer them. So now, I had told you in the very beginning that I am going about this entire course in a slightly more complex manner, in the sense that usually we would go over uh, chapter 1 first, chapter 1, 2, 3, 4, whereas I straight away delved into chapter 4, and then I had promised you that I'll go back to chapter 1. So that's what we'll do now. So we'll now go back to uh, chapter 1 of the book, where the chapter 1 is actually rather elementary in many senses, and except for a couple of few points, not much is new in that. And I've been already in chapter 4, I've already been discussing elements of chapter 1 to you in some sense, but still let us look over that. And the basic idea that that's forms part of the chapter 1 is the idea of the rigid body, right? So they go over the idea of the rigid body all over again, and they introduce elements of the Newtonian mechanics, some of which you are already very familiar with. And only towards the end of chapter 1 they introduce the idea of joints, which is the slightly the newer aspect of that chapter. So in chapter 1, what you have is you will have we are looking at, for example, a body which is not started deforming. So a body has many different forces acting on it. So you have, let's say, F1, F2, F3s, etc., etc., and these different forces, these are all external forces. Okay, so external forces. So when a body is in equilibrium, we know that the summation of these forces is going to be equal to 0, right? And we'll need to use this from here onwards, this equilibrium issue. And you already know that we are not in this course, we are not so much focused on motion of the body, but rather just on the deformation. So this this condition will apply very frequently. And similarly, as this applies, you also have summation of the moments which will be equal to 0, and this is a vector, of course, and this is again a vector. So in this case, you will, if you have discrete forces, then you will be able to sum over all the moment arms of this and for forces, and you can see that that will also, the moment will also end up to be 0, right? And for the moment, what I did is the book already goes over it, so I've just taken this out from the book. And the moment of a force about a point, so it is the moment of a force is defined. This is revision stuff for you, I hope, but still we are going over it. So here we are discussing the moment of a force about a point O, and this is the line of action of the force here. And to find that out, all you need to do is to just create an arbitrary point on this line of action, and find the moment arm. So this is r, which is a vector, and then the moment here is defined as r cross f, where r is the vector and f is also a vector. So here this is f, right? So the magnitude of r cross f is obviously f rf sine theta, where theta is this angle right here, right? So so this is how moment is measured, and couples as a special type of moment situation where you have an equal and opposite. So couple is formed when you have equal and opposite forces acting parallel to each other. Okay. each other. So, for example, you have an axis, just then you have a force, and then you have an equal and opposite force, such that there is a difference between the two. The lines of action, there is a difference, and let's say this distance is given as a. Oh, okay. Sorry. This distance is given as a. So, if you wanted to find out, so this is O, let's say. If you wanted to find out the moment of these two forces, then you could just take a couple of arbitrary points. Let's say this is some x1, and here on you could take some other point x2. So, the net moment for this case would be just x1 cross f. So, this is f, let us say this is just minus f, right. So, this is now minus x2 cross f, which is x2 x1 minus x2 cross f, which is nothing but I could so this is this a vector and then f vector, right. So, this couple is independent. Oh, I had enlarged this. Sorry. Okay. I didn't realize I enlarged it. So, there is more space here. So, the couple is independent of the choice of angle. And the reason couples are important is because they often come up in various mechanical situations where forces are generated by bodies which or many links which are in contact with each other. So, it is not uncommon to see them. And the reason we are discussing all this is because we will be discussing situations where you will have forces, many different bodies together come up or form a system, and that will result in forces in the system itself. And these forces are generated because through contact usually. You can obviously have forces without contact if you have, for example, electromagnetic forces or some other type of, for example, light impinging on some a body also can generate forces. Those are not under discussion here, but the kind of forces that we are discussing is let us say this is a link here, and this is a wall, and this is contact, right. So, so the forces are being generated through the contact. Okay. So, these are the kind of scenarios that we are interested in, and this is why for understanding of forces and moments in a given system of many bodies starts to become important. And you have for example the issue of links, right. So, where do different bodies come into contact with each other most often, and that is where in mechanical systems what we call as links, where things can come together. So, let us formalize this a little bit more, where force transmission can occur. So, forces through contact. So, one example is the example that I was giving you there, which is let us say you have a body, and then you have a link or something, or a member that is coming into contact, and uh, let's say, let's say that this is frictionless. If this is frictionless, then the only kind of a force this can exert is a normal reaction. Okay? So, in frictionless case, only normal reactions will be seen. Okay? And normal is normal at the point of contact. And if you have uh, a case where you have, let's say, friction, then so in this kind of a case, which is this friction is present, then you would have both a normal force and another force here. Okay. So then the two force can act in any direction at the link. So it can be broken up into an arbitrary. There can be a force in an arbitrary direction, and then of course, if that is true, then this can be broken up into a normal component and a perpendicular component along the wall. Right. Another type of contact is the frictionless pin joint. Okay. So this is let's say 1, this is 2, 3 is frictionless. Wait a second. Pin joint, and here let's say you have a couple of links that are in contact with each other. Let's say, and this is the pinned joint. Okay, so this is the joint. If this is frictionless, then you will have forces. It will there will be a force that passes right through the pin. Okay, so a force will pass right through the pin. So if I were to break this up into different links, then you will have F, and then on this link you will have a negative F, a minus F. On the other link, of course, I have not drawn the direction of this has gone wrong. This should be aligned with this. Forgive me for that. And this will pass right through the pin, but no torque will be caused. Okay, so frictionless pin joint is force passing through pin without a torque. Okay. So similarly, you can have a frictionless. So I'll do one more example, and then I'll stop here probably. Frictionless bearing. Okay, so the frictionless bearing. Say, so this is a frictionless bearing. So the frictionless bearing, it will exert a force on the shaft, which again passes. It's just like the pin joint, so it will pass to the center of the shaft, and no torque will be transmitted. Right. So there is this is a bearing. So there is maybe a rod that is passing right through it, and the force is such that there will be a force that is passing right through the bearing. So force passing through through the shaft that goes through the bearing, but no torque. no torque, just like the previous case. Okay, right. There are a couple of more cases to discuss, but today maybe I'll just stop here. So I hope we have had, I have been able to give you a good flavor of the Mohr circle today. And then we have just gotten started with chapter 1, which is something that you are very familiar with. We'll finish it in the next class. There's not really a whole lot of material in chapter 1. So please go over this, especially this particular derivation here, and please go through the examples that are done in the book. And also, of course, if you have not attended the tutorial class, then please go through that as well. That's going to be quite important. Okay, good. So what I'll do is I'll stop here today for this class, and then hopefully in the next class I'll see you in live. Okay.